our exercises. So the first exercise is an estimate to show that the genus of any knot is bounded by half of crossing number. So let us look. Is it okay? You see this or not?
Yes.
Okay.
Natalia, do you see?
Yes, I see.
Very good. Very good. So what is the what is the argument? Can you start, Raphael?
We just use the definition actually.
Yes.
And nothing more. So we recall. So what is the other characteristic in point of view of cells, for example? So we take this and ribbon, and yes. So in the cipher algorithm, we have that each crossing gives a ribbon.
Right.
Then by definition of the other characteristic, we then have the M disk that comes from the cipher surface, and we have to take out n ribbon.
Right.
That's just definition. And we have the other definition of of the other characteristic, which is 2 minus 2g minus 1 with g the let's say the minimal genus of the surface.
Right.
And then we just say that 2 minus 2g minus 1 is equal to m minus n, with m the number of disks and n the number of ribbons. And then we just solve and we are done.
Right. We also use that there should be at least one surface when we construct. When we construct Seifert surface, there should be at least one disk, and this is because we have one here, then we have exactly n, not n plus 1. Yes, very good. And then in the second, we have this interesting thing. So how should you operate? You are using the we can do this directly, or you are using the additivity formula, right?
Yes. Like at the end, to be sure. Yeah, to show that they are prime indeed. So the additivity formula is to show that they are indeed prime.
Right. So because I, as myself, I was directly calculating the number of surfaces and disks and ribbons in the Seifert surface for this. So
yes, it's what I did. Then we got a number, and this implies that yes, we got one, and by additivity, it implies that it's prime.
Okay, right. So Natalia, do you agree with this calculation?
Yes, I calculate genus of this diagram, and I think that's Taurus. And yes, this genus is one, and then we have primaries. I'm not.
Right. Right. We have that because genus is one, it cannot be divided. So we have prime nodes. Very good. Very good. If there are no questions, we pass to exercise 3. Actually, we did this, but I put it again in the context of our formula for additive formula for genus. So we were using what I forgot, the coloring or something like this. We were using the product of coloring, right? For and we also can make the sum of connected sum of trefoils, and the number of coloring gives you that it will be recoloring, that it will be distinct nodes. And the same here, that we can just have the sum of trefoils, and we can get the nodes with the different genuses when we make the connected sum. Actually, we constructed the granny node and the square node and the genus 2. So we have plenty of nodes. And so if there are no questions, let us consider actually this was this example was the result of our discussion that we had like last time about the Seifert surface genus, Reidemeister move, and so on. So let us consider the following surface. Natalia, did you look at this surface?
Yes.
So how can we calculate the genus of this surface? How can we calculate the genus of this surface? Who can ask about the genus of this surface? It's not so difficult.
One boundary, all line is one boundary. Yes?
Sure. Very good. Right.
And I see one vertices and two edges.
Right. So the genus of the surface is equal to
1 minus 2 plus 1. I think it is Taurus.
Yes, this is genus 1. So we have one boundary component. We can do this. Use this just going around. Okay. Then this way, this way, this way, and we were around. So this is one boundary component. one boundary component, one disk or 1 point, and 2 edges. So we have exactly, if we look at the formula, 2 minus 2g minus 1, and this should be equal to minus 1. We get that genus is equal to 1. So this is a torus, and then we shall define by Reidemeister moves what the knot is. Who can guess what is the knot? Just looking at the picture, and then we can try to look at Reidemeister moves.
I think this threefold.
Right, so we shall look at it, sure. This is a trefoil. Right, so now how can we construct the Seifert surface of this knot? Now consider, now forget about what is surface, right? Look only these lines. It should be like a knot diagram. We forget that there is a surface in between lines. So this is a knot diagram. So for example, here there should be arcs, okay? And this is crossings. And this is crossings, right?
Yes.
So this is a knot diagram. So not this, consider please that it is not ribbon going like overcrossing, but just 2 lines which are going over this thing, and here should be, which is not seen, but here should be the arcs, small arcs here, right? So how can we construct the Reidemeister surface? Natalia, can you help us? You are the specialist in Reidemeister surfaces. What will be the Reidemeister surface? We can start, for example, from here. Excuse me. No. Maybe like this, and start to make our pictures. So let us tell, for example, that there is a direction in this here, that it will be this direction, right? Here it will be like this direction, then here it will be opposite direction, here it will be like this, and here it will be like this, okay? Then it's okay. Then probably we shall see this. Right? Okay. So what? Please help me to construct Reidemeister, so it should be attentively done, attentively. This in opposite direction, and this is also this going this way, but here we have this. So what will be the Reidemeister surface? It may be like, if we go by this direction, it may be like this, here like this, like this, then like this, right? Correct if I'm not right. Like this, going this way, and then going this way, this way, this way, this way. This is the big disk, right? Natalia, do you agree? This is a big disk, right? Then let us consider the small disks. One will be here, two will be here, the third will be here, and again one is here, right?
Yes, and okay.
Okay. Very good. So we have 1, 2, 3, 4, 5 disks, right?
Yes.
5 disks. And 5 disks. And we have so 1, 2, 3, 4, 5, right? 5 disks. And we have how many crossings? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 crossings. So we have 8 ribbons, right? So this is -3. What does it mean? That the genus of Seifert genus of this Seifert surface that we considered is equal to it is like this. The genus of the Seifert surface is equal to 2. And as we calculated before, the genus of this surface is equal to 1. So this gives us the essential remark that Seifert surface, in this case, because it essentially depends on the diagram and the construction which follows from the diagram. In this particular case, gives us that the genus of this Seifert surface which comes from this diagram is equal to 2. So that's why in the definition of genus, you should consider all surfaces, not necessary the Seifert surface which comes from one special diagram of this, right?
Okay. I think it, and I draw what happened for the Sandan-Fan in this construction over the Meister move.
Mm-hmm.
I think that genus can change. I'm sorry, I'm not right in last.
It's okay. It's okay. Let us now see that why we can see that concrete. We can make this now. Let us to be sure. Let us simplify this. Let us now simplify this knot by Reidemeister moves to our beautiful trefoil. So let us now make to know to have so if there are no question, I can erase this. So yes. So, Rafael, do you have questions?
No, it's okay. It's okay.
So you see that the genera are different.
Mm-hmm.
Here is one, and but if we consider this as a knot diagram, we get. And now that this diagram, to understand concretely that this is trefoil, let us make a small exercise, and so consider now, please, that this is a knot. This is a knot, and let us apply. I can look at my notes. You can consider this like a knot, and now let us apply Reidemeister moves to this knot diagram. Again, consider please only this black boundary. Forget about the surface, and let us apply the Reidemeister moves to get a trefoil. Who can start?
Probably take the right handle and put it on the bottom.
I propose, no, just apply the Reidemeister move. I propose what is evident to start. This thing is the first Reidemeister move. Raphael, look at this. This is the, right? This is the first Reidemeister move. Here, you have a look. So really now the note will be the following, that forget about these. You have, sorry, I try to make a pencil. So it will be like this. Not forget that here is a line and it goes this way. Forget about this. It is like this. But here, not forget this undercrossing. Here is undercrossing. So, but everything is okay. So, what do we do? What do we do? Here, what is the next move? Natalia, can you help us? I'm looking for my notes.
I think I try and draw picture.
I suppose that I was doing the following thing. I couldn't find my note, but maybe to apply Reidemeister to move this way.
I can try.
Yeah.
Okay, I can draw my picture. Okay.
Mm-hmm.
Oh, sorry.
Okay.
Good. Okay. Let's try this loop is
Yes, we already eliminated it.
okay. We can rotate this loop. Okay. Yes. It's okay.
But we already eliminated it. We just forget it and we put the line like this. So look, there is no more here. No.
Yes.
You go directly here.
It's okay. Yes, this line and this line and this line, and this is a simple loop, not?
Okay, but we already simplified this loop. It,
Okay. Okay. Sorry.
But then I think I was going because everything is over. I was moving this line to this direction, right? So maybe something like this, and then we'll simplify. No?
I cannot see in this picture anything. Sorry.
Maybe I should just try to find my.
Okay, maybe let's try move this line.
Which one?
Maybe try move this this line.
Yes.
This line up. In this direction, down of this line and this line, we can move this on this direction. This line down of this line and down of this line.
Mm-hmm.
Maybe draw another picture without surfaces. I can if we.
Yes, can you please? We can look. There is a space to draw it.
Okay, in this space,
Yeah, please.
we have,
You have space here, right?
okay, this is our,
Right.
yes, we uncrossing this loop and we have,
Right. Very good. Very good.
no. This, and it's okay or not? Yes?
Yes. Yes, because there was this ribbon was going over, right? So this is undercrossing and this is overcrossing. This is this is undercrossing. So we should raise a little bit. Okay. Yes. Very good. Yes. Yes.
Let's try third or the master this line and this two line.
I don't see your.
Oh, okay, sorry.
I proposed at first what I remember to move this line.
This
No.
this
I
line.
proposed to move this line to make it over here.
Okay, let's
To
try.
move this line over here, Natalia. Look. This big loop make over here.
This loop.
You see what I'm pointing? Yeah, exactly. Let it be like this. Here.
In this direction.
Yeah. It should cross exactly when you are what you are showing. It should cross like this.
Yes, we have this.
Exactly. No. No. Just to show that from this point it goes here. We do all these third Reidemeister moves by this and by this. So like this. Okay. So can I also try to make your picture this, right? And erase this stuff, all this stuff, right? So look, we have this stuff, and now we can erase this thing because it is overcrossing. Use again second Reidemeister.
Yes.
So erase this one. what do we have? I forgot what I erased. So
It's very difficult.
like this, right? And that's all. No? Not that's all.
I cannot see
Yes.
in this picture because our note is empty.
No, no, no. Look. Look. Before it was like this. Before it was like this, right?
This line is where is second part of this line? Or,
this is the second Reitermeister move.
Oh, sorry. This line where is second part of this line? I don't understand.
Right. Right. I don't see what is happening. You see something disappeared, right? Natalia?
Yes, all the draw disappears.
Yeah, I'm sorry. So, but now when I remember, I can tell you what is happening. So, at first, we kill this.
Okay.
We kill this. We are making this thing. This is becoming our knot. Okay?
Okay.
Then we are killing this part. We go formally, Reitermeister third. We go by this line, by this crossing, and this crossing. So it means that we are doing this thing, right? So
yes.
This line goes over
Goes up.
Okay?
Okay. Okay.
Okay. So what is rest now? So see this line. Look, please. This line, starting from this point. It is always overcrossing, right?
Yes.
And this, because this is absent. There are no this line more. So it is, this stuff is always overcrossing. So we just making, because this doesn't exist, we are making this stuff going this way. Right?
Right.
And that's all. We have a knot with 3 crossing, right? 1, 2, and 3. Right? Or not yet? No. This is, we need to, no, sorry. This is okay, but there is still crossing here. This does not exist. This does not exist, this does not exist. Aha. But No, we shall do something here. Excuse me. So we have, but no crossing here. This goes without crossing, going this way. No. This. You have two crossings here. Then you have one crossing more. So something. What should we do with this crossing? So you going this. What to do with this one?
Расцепление сведется к учитыванию
Yes, we now can, because here we are here, we can use second Reidemeister to put here to here, and we eliminate this crossing. We eliminate this crossing, right? We eliminate this crossing, and right, sorry. Yes, this line, no, this line still exists, this undercrossing, but this is, no, this is overcrossing, right, overcrossing. Okay, I'm sorry, I forgot how I made this. It was so clear. So, Natalia, can you do this finally or not? If not, we can move because not to lose time.
I cannot, I try, I draw my picture, but I cannot result.
Okay. So yeah, it was not, it was quite simple, but there was almost a week and I forgot details, sorry. So, if you don't mind, we shall move to our next topic. But anyway, it is trefoil. So, okay. Today is the fundamental group. We are studying the fundamental group of knot. This will be our topic. Okay, so I just need to put but we didn't finished the previous thing and the interest of the Taurus links. Right. So Taurus links are produced the following way. You just take a pair of integers, R and Q, and you suppose that R is positive. Then consider a cylinder with R strings running along the cylinder and twist this cylinder for 2pq over R, so the angle. And the sign means that you are doing this whether in positive direction or in negative. You can just look at the cylinder and then make this twist. And then glue the ends. The resulting link is called TRQ and is formed like this. So this is our cylinder, right? If you glue these two surfaces, you get the torus, right? So, but now you take R, how I call them, lines or intervals, sorry, string, yeah, R strings, very good. So suppose that you are a musician and there are R strings. So this is A point. They join just parallel. Everything is well done geometrically. This is the R strings, alpha 0, alpha 1, alpha k, alpha r minus 1. And then you rotate. And then you rotate with the 2pq over r. Okay? And then glue the same way as before. And this is how we make this rotation. Say A1 is going around the cylinder and goes to B1, right? A0 goes to this direction, and A2 goes to B2. Now you glue this and this. If you glue, then you get, for example, if you are doing this, you can get a trefoil. 2R, this is trefoil, and the next one, cinquefoil, is you get 2. So if n is the greatest common divisor of q and r, then there will be n components. In particular, you get not if the greatest common divisor is equal to 1. Then you have a knot. In this case, you can make the following construction. So the construction of the torus is that you consider R2, you consider the plane. There is integers 2 times z over there. And actually this is abelian subgroup of this abelian group. This is a group and this is subgroup. So you can see the torus as you make, say, this is our R2, and here is, in this point, you have our wonderful Z2. Okay, so torus is a abelian group, which is equal to R2 quotient Z2, right? So actually this is the same. R2 you can consider as a product of two lines, and this is just a doubling of this construction, that if you just have a line and make a quotient by Z, then you have a circle, one, right? So torus is a product of two circles, so you are doubling this construction. Geometrically, you see that these points are equivalent because the difference these points, say this is 1, this is 2, this is 1, and this is 2. These 2 points are equal because the difference is equal 1, and these points are equal, and we have the same construction of torus as we are identifying this interval with this one. They're equivalent because the quotient Z. So this interval is equivalent to this. This is equivalent to this, and we should do this in right direction, right? So, and this is exactly the construction. At first, for example, by X, you just take the X axis and you make a cylinder, and then you glue these two circles and you have a torus. So in this construction, if you take now line, it goes, for example, let it be like this. You take a line and say 2 here and and 3 here. You see that this line actually, because after a short period of time, it comes to this point. And in this identification, they are the same. 1, 1, 1, 0, 1, they all the same because they belong to the integer numbers. They are all equal to 0 point. So the same you see in the torus, that this point is equivalent to this point, this is equivalent to this, that all 4 points are just the same. So all the vertices of Z2 are just the same. So here, your line is not touching the initial point. We suppose that our direct line starts from 0 and goes, say, let it be P and Q, or R and Q, we make this notation. R and Q. And so if and this is equal to Q to R, right? Q to R. So this line, when we are factorizing by Z2, becomes a circle, because this point meet with this point. So in the if we see, for example, only this square, this point is equivalent to this one. So we can, in the same square, if we are now concentrated in this square, we can make a picture like this, goes to this point, but this point is the same as this point, right? This point goes to this point. Then it goes to this point, right? And this interval is equivalent to this one, but this point is the same as this point. So we up and we came here. So excuse me for bad drawing, but these intervals are our intervals that are in the plane, but really they are in the, and so it means that this is our torus. This is what is happening in our torus. So, and we have, if we make drawings, then it will be the knot in the torus, right? And in particular, we get 2, 3. This will be trefoil. Trefoil is a torus knot. So this is, but if you want to construct a link, then you need to do several lines. The number of lines should be equal to n when you are making our construction with the cylinder. So, other question at the moment?
All is okay.
And so, Rafael, question that you should know in your previous courses. What will happen if this number will be irrational? If this coefficient of this line, so you say you have y equal to alpha x, and
it's dense, no?
Sorry?
Dense. It will make all the.
Yeah.
Mm-hmm.
Right. We'll have a line, and it will be the curve, the infinite curve, curve of infinite length in the torus, and because this is rational, we see that it will never be in the integer point, by definition of irrationals, and but it is standard exercise in elementary topology that it will be dense in the torus. But our objects are more beautiful. They are not dense. You just have a curve in the torus, right? So, okay. If there are no questions, we'll finish with these. Finish with this, so some remark that sometimes you may meet the torus link when you have, for example, you may have both two integers may be negative. So what does it mean? If we were starting with R strings, right? We were starting with R strings. So what does it mean? That mean that, look, our construction was without orientation. So we just consider the intervals that they were glued together, some points in the bottom to the top, and we got an object without orientation. So, but if you want to have an oriented object, right? So you should make you should do orientation. You should make orientation in this you should put orientation at each arc, and then you'll get oriented knot. And if you make just by condition that you make this orientation of your intervals, you'll get oriented link or not in torus link. But if you put opposite orientation, then you at your torus anyway you have your torus link. Without orientation it will be the same. For example, the same trefoil, and you have the same trefoil but with another orientation. That's all. That's all. This means that you have it means that you have torus link with negative R, and you can make this to negative. It means that if you negative, you make so if there are no questions, we'll start with our fundamental group. Today our aim is to define the fundamental group of link. So it need to be, I put something in the text. So what is essential? Essential here is that you take a loop. So if you have a space, say space X, and you have an interval. Essential is that when you consider fundamental group, say this is our space, like this whole, essential that you have a starting point. And you consider a loop, then another one. So this is, let it be alpha, and this is beta. And then what is the multiplication? It's evident that as we consider loops, all loops go from interval from 0 to 1, then you should go with double speed, all these guys. So this will be, by definition, the product of these loops. Okay. So you can define a product in the set of loops. And this is the essential thing for the fundamental group. And you can define a homotopy. I will not speak a lot because we were already studying the isotopy a lot. Then fundamental group, this is loops, but you consider them with the up to homotopy. And only this up to homotopy gives us the group. So formally, if you have, for example, if you have a loop, and so this will be a loop in your space, and here another one, let it be, so this is alpha, and this is just a constant. I denote it as so formally, this loop, which is a composition, is what? You are going half time this way, and then you are standing. And if we define as a neutral element the loop which is always constant, then this this, which is half alpha, half constant, is not equal to, as a product of loops, is not equal to alpha, but up to homotopy. So if you consider alpha here, and here alpha and constant, you just consider the following. If you consider the following, if you'd like to have the homotopy, then this is our constant. This is alpha, this is constant. This is alpha everywhere. So you see that this multiplication has neutral element, the constant loop, only if you pass from loops to homotopy classes of loops. Then this multiplication will have unit. The same way it will have the neutral element, the inverse element. Say, if you have alpha here in this direction and you have alpha in this direction, then you should make the following construction, something like this, right? Then here you will have that at this you will have constant. So the formally, what is the product of alpha and alpha inverses? You will go alpha, say this way. You go alpha and then alpha minus 1. You are not going to run this and back, but up to homotopy, you can go this way, and this way, this way, and this way, and finally this is homotopy to. So the set of loops becomes a group, and associativity the same way becomes a group only when you pass to homotopy. So this is sometimes called first homotopy group or fundamental group. Okay, very good. So this is that the fundamental group behaves correctly under map. So this is also geometrically evident. You have a space X, you have a space Y. So if you have a continuous maps between them, then any loop by continuous map goes to loop over there. So, and everything is okay up to homotopy. You see that then the fundamental group from the space X, but be careful with fixed points. You should have f of x0 is equal to y0. So you have that your fundamental group goes from here to here. This is one wonderful and beautiful feature of fundamental group. Other questions at the moment?
All is okay.
Very good. Very good. So this is how behaves the fundamental group. So some definitions that connected by arcs topological space with trivial fundamental group is called simply connected. So this is something if you have a group, say G discrete group, and it acts, then the fundamental group is isomorphic to G. So maybe this will be this example, and then our Taurus example. So let us consider the construction that we have. Let it be that this is our line, and then the group Z acts here. So by if you have a real number R, then action is by R plus N. This is the action, and then the fundamental group of the quotient space. The quotient space, as we discussed, it is circled. Then the fundamental group is Z. The same way here, the n-dimensional torus. So everything what we were speaking about in R2, possible to say in Rn, and then you have that torus is the fundamental group is just that n. But our case is that we consider just 2. fundamental group of our torus is just this one. This is about the surface, non-orientable surface that if you have RP2, this is Möbius band with disk. So then this will be that too, because as we see, this is the sphere, and Z over 2 acts by antipodal points. So the fundamental group of the sphere is 0, and action Z2, so the fundamental group of projective plane is Z2. By the way, what is the Euler characteristic of projective plane? What is the Euler characteristic of projective plane?
-1, no?
Why minus?
We have one cell in dimension 0, one cell in dimension 1, and one cell in dimension 2.
Right. So it means 1 minus 1 plus 1. Okay.
Oh yeah, sorry. Yes, 1.
Yeah. So also you can calculate this way. For example, we saw that the Möbius band is
It's a disk and a Möbius band. Yeah, as well.
And distance. Okay. So very good. Very good. So this is okay. So, but your calculation with projective plane is excellent, because you have cells in each dimension. This is very geometric calculation. So, and we will need the following Seifert-1 compensator. Actually, it was considered by the same Seifert who, sorry, I again made a click in something wrong. Sorry. Yes. This is Seifert-1 compensator. So it is the same Seifert who constructed Seifert surface. And maybe it is complicated by theorem, by topological spaces. So maybe it's too general. We can, I just explain how to calculate using the Seifert-Van Kampen theorem maybe I give an example. The example is the following, that let us consider this object, which is a bouquet of circles, right? So we know that this is Z, this is Z, and Seifert-Van Kampen theorem says us that the fundamental group of this will be you should look at the intersection of these two circles, how they intersect. So intersection will be, if you consider closed variant, then you can consider just one point. If you consider topological spaces, then it is safe to make this cross in as the intersection. So it may be for topological spaces, Seifert Van Kampen should be a circle with this stuff, to be open space like this. But anyway, Seifert Van Kampen theorem gives us the possibilities to say that it will be this and the free product of two cyclic group, two infinite. So this is a free group of rank 2, not just sum, but a free group. So if you have a free group, you have A and B, it is not equal to B and A. It's not equal. In Taurus, they are equal, but not here. And this means that, and geometrically you see that if you go this direction by this loop, say A, and then you go by this loop direction B, and then to see if you make multiplication by the left, by the right from here, you have A, B, A minus 1, B minus 1. It will be not equal to constant, and you see that A, B, A minus 1, B minus 1. You see that this loop, geometrically, you see that you have no possibility to shrink this. So this is a free group. Other questions?
All is okay.
You met before, free group, Raphael?
Yes, of course. Thank you.
So this is very sketchy about free groups, and yes, so this may be done, and you can get free group of any rank, maybe infinite one. So this is that fundamental group. That fundamental group, as we are considering the surface, the boundaries. So our picture, how we were making the closed surface, that you are making the to and gone, and then you make a identification, and identification, you glue a cell, and this will give you that this is the edges of N2 and gone, here 2G gone. This will be the genus of the surface, and this is the cell which is attached, and you have this relation. So this is our picture. So if you have the N gone, so you have say x1 in this direction, then y1 in this direction, then you have x1 but by this direction, and then you have so I write x minus 1, y minus 1. So in this direction we are going. Okay, and this will be the cell. So you have the cell which corresponds to the boundary of this, and but boundary only in the picture. When you make all this identification, you'll get a surface without boundary. So, and this is the fundamental group. So how can you prove and identify what will be the fundamental group of the surface with one boundary component? How can you now identify that what will be the fundamental group of boundary of fundamental group of surface genus G with one boundary component? Natalia, can you help us how to identify this group?
What is the question?
The question is how to identify the fundamental group of surface of genus G with one boundary component.
Okay, we can take 2n1 and glue together pair of sides.
Exactly. That's what I make a picture here.
Yes, and in your picture we have x and y is our loop in fundamental group. All vertices in this picture glue in one vertex, and we take this
exactly
point.
Yes.
So our start point in start of our loops. Okay?
Right. And so what will be the fundamental group if we just make one boundary component for our surface? What will be the fundamental group?
Is equal. We can move this loop in point.
No. The fundamental group, if one boundary component, will be just the free group of 2G.
Okay. I think that one component glue one face.
Yes.
Sorry.
Yes. So the proof is the following. You put this boundary component here and now make the deformation. Make the deformation of this central circle to the boundary. From the point of view fundamental group, it is possible to do because fundamental group is defined up to homotopy. Then when you kill all this surface, and what is left? Only the n-gon with identifications. So x1 this is identified with this, y1 with this, and as you absolutely true, you told, and this is essential, that all the vertices of n-gon are identified with 1 point. So what do we have? We have 1 point and a bouquet of 2G circles. So homotopically, the surface of genus G with 1 boundary component is equivalent to the 2G circles, right? And we get a free group of genus 2G, right? For example, you have Taurus. You have Taurus. You make a hole in the Taurus, and you get a group you have a group, free group of 2 generators. And if you remember our surface that was in the exercises, what is it? The disks with 2 bands, right? This is homotopically the same as the wedge of 2 circles. These ribbons gives us the wedges, and this is exactly 2 circles and genus 1. So we should have the wedge of 2 circles, and the fundamental group of the surface that we considered in our moving in Reidemeister moves gives us free group of rank 2. Okay. So this is about the free group. If there are no questions, then about groups is maybe it more or less standard topic. Yeah, this is about fundamental group because you need to make identification. This is fundamental group of non-orientable surface. This is another stuff. So something about the covering space. So Natalia, did you meet covering space in your life?
Yes.
Very good. Rafael?
Yes.
So, very good. So we need that. So typical example is exponential map. Actually, probably everything started with this. We have a circle, and you have R, and you have the exponential map from here to here with usually standard it is saying that exponent of 2p e x of phi, anything. So, but there are other examples. There are other examples. the complex, this is the finite if you consider the complex map Zn. If you consider again Rpn, you have a two sheet covering the group. Okay, so it has the path lifting property. I wrote down, if you want you can read, but I think we don't have time to do this, and probably, if you don't mind, we shall start. We need one more preliminary topic. This is about algebra and presentation. So our aim for today is the Wiltinger presentation for the node group. So sorry, I'm not okay. So this one. This is finished. So we need something about presentation of groups. So you consider a set which we call alphabet. The sequence of elements of the alphabet is called a word, and there are evident things, the length of the word. If you have a word, then evidently this word is called inverse. We can define the product of juxtaposition. You have one word and you write down the next one, and this will be the product of words. So the aim of this stuff is to make the encoding of elements in a group. So a word, if you have a word in your alphabet, and if you have a map, say, suppose that you have a map, and this is the so the set. Yeah, so it is if you have alphabet A and you consider all the words, you may call them as a language. And if you have a map from language to group, language is definitely monoid by juxtaposition. Then you have a homomorphism of monoid, and an element is called relator. The word is called relator if its image is a neutral element in a group. So it's only, I think, mathematical word. I never met this word in English, but in group theory it is standard term, relator. So it means, yeah, so evidently that if you have such words, they are evidently relators, because if you map A to any element in a group, A minus 1 is mapped in the other, in the inverse element, and the product will be trivial. They call that trivial relators. So two words W1 and W2 in the language, they are called equivalent with respect relators. fixed before, if you can make an insertion of the relator or its inverse, or erase them. And the word W is called derivable from relators or any words if you can do this operation 1 and 2 and go to empty word starting with your word W. So if you have suppose that you have an alphabet for encoding G, and each relator is derivable from the given set of relations, the relators, then it is say that they constitute the complete set of relators. So if you have complete set of relators, then these are the generators. I forget to tell that generator means that if you map all of them, you get an epimorphism of language to your group. So this gives a presentation of a group. So generators and complete set of relations. Yes, so we return to our favorite free group. So then, what does it mean, free group? You have n. We are interested in finite number. You take finite number generators, and that's all. No relations, no relators. Only the trivial relators means that A, so say something like word W multiplied by word minus W. W minus mod, sorry. So the standard finally generated, finally presented. Then the evident theorem that if you have a presentation, the cardinality of all this stuff may be arbitrary, no problem. So then there is one group up to isomorphism which has this presentation. Simply consider all words of these generators and make the equivalence due to this set of relators. In this, so the language factorized by this will give you the presentation of the group. If you, this is a proof. And so this is the universality property. So this is maybe two annoying things, but this is the teacher transformation of one presentation to another one, how to do this. Why do I wrote down this annoying stuff in details? Because they correspond to like Reidemeister moves, like Reidemeister moves. So this is like analog of Reidemeister moves for for algebraic context. So what essentially the teacher transformation means for the presentation? You have a presentation, and suppose that you can write the words in these generators, the words ST, which are derivable from P, Q, R, and so on. Then you can add these words to the relators, evidently. Right? The same way you can delete. So T1 and T2 is the inverse. And something is happening when you can make, if you have some words, you can make extra generators, and you can name these words and add this to the list of relations. Almost the same you may do with some other stuff, which is the Titze transformation. All of them are evident. All of them are evident transformation, and evident that the following things, that if you have presentation, and you just, for example, you just make a word from P, Q, and R, and you add this word here, the word derivable from them. Of course, you will have the same group, only the description of this changes, but it is the same. So this is quite evident thing. Another which is not so evident, and I wrote it down because it is analog of the Reidemeister moves. So this is so I recently printed out that this is the fourth typographical. So here should be only one paragraph. Okay, so what does it mean? If you have the presentation of a group and another one of the same group, isomorphic if you want, and then one can be obtained by a finite number. I didn't wrote it. Repeat it. I didn't wrote it. Finite. Essential is that it can be obtained one from another by a finite number of Titze transformation. So this is complete analog. So of course for groups and these letters, words, it's annoying, but you can have in mind Reidemeister moves, and you say that this is complete analog of Reidemeister moves. So if you have what it will be the analog of for knot diagram, you have diagram for this knot, another diagram for this knot. Then if the knots are the same, then you can obtain the second diagram from the first by a finite sequence of Reidemeister moves. So this is these are the analogs of Reidemeister moves. Okay. This is something about algebra, and so if you don't mind, we can make a short break and start with in 5 minutes, and start with our study of knot group and Wiltinger presentation of this group.
Okay.
5 minutes. 5 minutes break. Okay, shall we start?
Yes.
So we start considering the fundamental group of link. This is the link complement. So we start with considering a link in R3. This is the first approach, or S3, and you consider the complement, the space. If you want to have a compact space, then so if you just take R3 minus L, it will be not compact. But you can take S3, which is 1-point compactification of R3. This is a compact 3-manifold, and you can take a tubular neighborhood. We were considering this in when we were looking at polyhedra, and so N is topologically solid torus. This is not with solid torus, actually, right? So, and ML, we denote the complement of in S3, the interior. So interior of N is an open space in S3. Complement is closed set in, actually it is a manifold. This is 3-manifold with the boundary equal to torus. So the complement ML is the compact 3-manifold with boundary homomorphic to torus. So we take the point, in ML, and by definition, the fundamental group is called the knot group, especially when K is the knot, then this is called the knot group. So this is the fundamental group of this complement. So this is what, okay, so let's diminish picture, right? So you see, you take pi 0, the point, and this is a knot in a space. At the moment, this is actually showing the idea how to calculate this part. Let's just consider that pi 0, and you considering the loops. You considering the loops which are going in the complement of a knot, and this is the will give us so so again we shall consider the division of our diagram. Say that suppose that here everything is happening in R3, and maybe, well, the diagram is in R2, in the plane R2, But maybe better to make a picture is the following: that these bold lines should be in positive. We call them BIs. No, this is AIs. They are in the upper half space, and these things are in the lower half space, and just these points of intersection are in the plane of a diagram. So this only these points they belong. So all the crossing are in the positive, and the crossing are in the negative. And here are the points when overcrossing meets undercrossing. They are all the real intervals in the R3 space. Okay, this is overcrossing are A1, AN, undercrossing B1, BN, with the space B and the space, and these guys are in the upper and these guys are in the lower. So with them, we'll consider the standard Wiltinger presentation, a Wiltinger presentation for the links. So I don't know why so we can consider them the arcs as before. So now I make the labels X. Usually they are labeled that X1, then you are going by the following the direction of the node, then X2 and so on, but not necessary in the crossings. So usually in the crossings it should be, if this is XL, then this should be XL plus 1. But in general, you can rename anything how you want, anyway how you want. So consider the crossing. Consider the crossings. And the arcs, say the arcs which are overcrossing arcs, they which are in the half space, they should be the generators. And the arcs which are going under, the undercrossings, they should be the crossing points, better to say. They correspond to relation. So around each crossing point, please write down the square. Please write down the square. And write relator in the following form. So maybe to see both, I make it smaller. Okay, no, bad idea. Okay, so yes. Do you see both? Oh no, sorry. I need that you should have you should see both. You should see both. This thing and relator. You see relator here?
Yes.
So you start, for example, with xk. you start with xk, right? And then you go in your diagram, you should go in the positive directions. So this means anti-clockwise. So you start, for example, because everything is cyclic, so you can start at any point. But usually people are starting with the things that go first goes from the crossing point. So I start with xk. If it goes out of the rectangle, then you put in the degree -1. So here xi goes out, then again -1. xl enters the square, then plus. And this xi again enters, then plus. So for each thing, then you have the following relator. It may have so the crossing, as you know, may be of 2 points. So here, all the crossing is going to the arrow of the undercrossing, which goes out. This is the negative crossing. Here you have this relation of this type. But you know that there may be crossings of positive type when the overcrossing goes to the arrow which goes out, goes to the so this arrow and this arrow, they go to the positive direction. Then what should you do? Then you write if you so actually I wrote in this sense. Excuse me. It be so better to say usually working with relations. So if it is negative crossing, then you should take xk is equal to xi minus 1 xl xi. If you have positive crossing, then the same xk you should write down xi xl xi minus 1. Maybe I made a mistake here. So this is what usually I'm writing. So this is for positive crossing, you start with xk and you take the positive xi. So you have conjugation starting with positive. So the Wiltinger theorem is the following. If we denote each relation like this, so you have crossing and crossings as we see, and you start, and at each crossing you have a relation, either this one or either this one. So we denote each relator by, or relation, anything you want, by Ri. Then we have the following presentation exactly in the sense that we discussed. that the group is generated by Xi and has n relations corresponding to each crossing. And one speciality of this presentation, that you can erase without any problem any relation, but just one. So in reality, it has n generators and n minus 1 relations. So the proof is given by you considering several spaces and using the Seifert-1 Kampen theorem. But it's quite long. I just only want to make some explanation, maybe non-formal, why this relation hold. So suppose that you have a loop going like this and returning to the same point pi 0. So we start with our point with somewhere up on our plane, and suppose that your diagram of a knot is on your desk, on your table, and the lines AI are going over the table. The BIs are under the table. This happens under each crossing. And your loop, which corresponds to the generator of overcrossing X, is just going this way. It goes under this arc, which is just on your table, arc AI. And this loop starts with pi 0, going to your table, maybe it's because really this arc is up your table, and returning back. So this is the only way that the loop corresponding to Xi is doing. So what now you have in mind this picture, and return to this picture. Return to this picture. So what does it mean, this rectangle, this square? So suppose that this star is your starting point, and you go vertically. You go vertically from your starting point, which is, if now this is the plane of your desk, of your table, then your point pi 0 is between the table and your eyes. So then you are going this way, and you are going this direction. No, at first you're going this direction and returning. Then again you're going this direction and returning. Then you're going this direction and returning. This direction and returning. So now if you make the composition of the loops just what we were considering today. So what does it mean? You start here, but suppose you just came to this point, and this point is on the desk. You're going on the desk under this arc. And then you return and go back, but this you can omit because it's coming back. Then you go this way, and then again you're going to the starting point and return back. But you can simply continue going this, following this rectangle, and you are returning back. So it means that these four paths, all of them are going, if you draw more convenient picture for you, then it means that your rectangle is all the time under your knot. Suppose that you do not meet this crossing, it happens somewhere over there. It all under, and this loop which came to this point go by this rectangle, which is completely under the knot. It is under here, under here, under here, and under here. So it is like in Reidemeister move, which is always under the picture. Then you can deform. I can try to draw pictures. So you can now, if this starting point, you can now deform your rectangle, and everything is going under this knot, because this is under, this is under, this is under. You are going under, you can deform, and finally you can escape your knot. And if you have your starting point is in the interval from here, or maybe I can let it be in the space. Let this be starting point. A little bit different projection. So you came here, and then you go this way, and this way. This was your initial move, but loop. But then, because everything is happening under the knot, you can deform this way, you can deform this way, you can deform this way, and finally your loop is the following. You come from point P0 and you return back. Evidently, this is the constant loop, and you should have the product of this axis, product of these loops, which correspond the generators. They should be equal to 1 to the. It should be equal to the fixed point. So this may be proved strictly. So this is the problem is in the proof, as usual, to see that there is no other relations. This is as usual in the group presentation. Relation you can obtain more or less by these or that arguments, but to show you need some hard, heavy artillery, and this is Untitled Theorem that I mentioned. Other question in this not in this maybe non-formal explanation. Other question? Natalia?
It's okay.
Do you have question?
Oh, my internet. No, it's. I think it's clean.
Okay. Okay. So this is the. So this is the. This is the. This is the. Vertinger presentation for any link. And of course, let us start with our favorite trefoil. So this is our trefoil. I always, yes, this is, I think, left trefoil, right? So these are the, I should make more. Yes, so maybe even more. So even more. So no, unfortunately, the picture is the letters are small. So this is X, this is Y, this is Z. Do you see? X, Y, Z. So X goes out of this rectangle. So X minus 1. Then this is Y. This is Y. This is direction of Y. Here, Y goes in this direction. Y goes in this direction. It enters. So it should be plus. Here we have Z. Z enters, so it should be plus. And then Y goes out of rectangle, so it should be minus 1. The same way in all three you get this relator. So it is positive. So if you write in the form X is equal to Y, Z, Y minus 1. All of them are positive. This is the positive, right? So we have 3 relators. So this is the form that I usually write down. You see that X is even Y, Z, Y minus 1, Y is equal. So how do we operate? We put X, so we apply it's a transformation, but if you may not use this term, we are using evident transformations with our presentation. So you put X equal to this one, and you put in 2 other relations. So you see, right? No, you put, no, I have Z. This is, I'm looking at X, and actually I wanted to get rid of the letter Z. So you put Z, what do you have? X is equal to this one, Y is equal to this one, and formally you should write down Z, but using the Tietze transformation number 3, I think, you can get rid of this because it's just Z equal to a word. You can write or you can erase the word. So you have just two relations. X is equal to this one and Y is equal to this one. Now, right. Now how to prove that they are essentially the same. You make the second relation, you multiply by this stuff on the right. So can you see? You multiply it by the right. If I'm correct, then you should obtain the first one, no? No, maybe I'm wrong. I'm maybe wrong in calculations. Look, I wrote down and X, Y. No, it's okay. It's okay because you after that you put yes, but then we'll X, Y, X. Yes. Yes, and so in particular, you see that that one relation should be erased. This you see in practice. So you have this one, and then now you may, if you want to have more beautiful relation, you make multiplication by y minus by y here on the right, x on the right, and you have this form, right? So you have this beautiful form of this group generated by two elements, x and y and one symmetric relation. Okay? Is it clear?
Yes.
Rafael?
Yeah, yes, okay.
Okay, a bit more complicated again. Look, maybe I'm making mistakes. No, I made the wrong picture. Figure 8. I simply doubled the picture. Maybe I. No, I make correct, I suppose, correct calculations. No, I make, yeah. Yes, I'm a little bit wrong. But finally, this is quite complicated, but this is the group relation for the figure 8 knot. Okay. And anyway, because I gave not absolutely correct proof of the Verchinine presentation, I will make now the proof, but from point of view of combinatorics. So I'll give the combinatorial proof by pictures. The real proof, actually also the sketch, because we don't have much time. But this will be absolutely strict. So let D be a link diagram of the link L, and let be the Verchinine presentation of the group. So you just consider a link. You consider a diagram. From diagram, by the algorithm that I told you, you make orientation. At each crossing, you are making square. According to this square, you are getting relations, and this will give you a group. So absolutely combinatorial stuff, no topology. But anyway, this construction is correct by itself. So we have the following theorem, that if we have D a link diagram, and this is the Wiltinger presentation, this is the algorithm that we used, and suppose we now try to make Reidemeister moves to this diagram. Then, of course, the crossing and the diagram will change, and we have another presentation and maybe another group. But this theorem is saying that if we apply Reidemeister moves, or one Reidemeister move, it's enough, diagram B, then the corresponding Wiltinger presentation is obtained by the application of the Tietze transformation to this Wiltinger presentation. So the group, as you remind our Tietze transformation, they do not change the group. So the group will be the same. So the group defined by this presentation is invariant of a link. So we now can formulate this a little bit different. So suppose you have a link L and its diagram D, but just by other projections anyway, you get another diagram D prime. But we know from theorem don't know, maybe it's called Rademacher theorem, that the diagram D and the diagram D prime can be connected by a sequence of Rademacher moves. Then if we have two Wiltinger presentations for these diagrams, for these nodes, we can join them by this theorem, by the sequence of teacher transformation. So the group obtained by the first recipe will be the same as the group obtained by the second diagram and its recipe. So this is completely combinatorial proof of invariance. So the proof will follow. So the proof is by pictures. So I even didn't wrote down the corresponding, but we can write down it together. So what does it mean? Here you have X, you have generator, maybe you have, you have a presentation where you have X is a generator and maybe some other relators. Here, after Rademacher 1, you have maybe generators the same, but you have one more, X and X prime, right? X comma X prime. And we have one more relation because we have a crossing. So what should we do? We should make a picture of our crossing and move in positive direction. So this is orientation of our loop, of our link, part of link. So this goes in this orientation of a crossing goes to this in negative. So what it should be? This is X. So X is equal to this is which is going from this, from the crossing. This is X prime, X prime going for this one. But type of crossing means that we shall start with the negative factor, and this is X, so it should be X minus 1, right? So then actually this is the same, because there are no here, because of the nature of this Rademacher move, there is nothing here, no interruption. So this, and it enters, so it will be X in positive degrees, right? X in positive degrees. And now our part of this stuff is entering. So it also should be in positive degree. And what is it? It is again our X. So it should be X in positive degree. So this is how this triangle, this rectangle works here. So what should we have? Of course, x minus 1, x disappear, and we have a new relation. So we have this, without x prime. Here, for this diagram, for the new diagram d prime, we have x prime, all the, so suppose that these are divided, these are relators, so these are the same relations that here, but comma, we have one more relation, x prime is equal to x. Even without knowing about Titze transformation, this is a typical example. You see that this group is exactly the same group. So you see that Reidemeister 1 changes presentation, but the presentation is the same. Presentation is Titze equivalent to this thing. Okay? Natalia?
Yes.
You are our specialist by Reidemeister moves. So you agree?
Yes, I agree.
Very good. So we have no time to write down. I just only show, and this will be the first exercise. The first exercise we have now this tradition that to write down the relations for this. You have here just x, y. Here x is the same, but because of Reidemeister 2, it is divided into three. It is broken in three parts. You have y1, y2, and z. So please write down new relations. So here you have now 3, 1, 2, 3. So instead of x, 1 disappears. No, instead of y, sorry. Instead of y, 1 y disappears. There appear 3 new generators and 2 new relators. Please show that they are Titze equivalent to the previous one. And of course, if you will be interested, and maybe you have just to practice, please do the same, because it may happen. It may happen that we have that all our nodes are oriented. So it may happen that these guys that have Reidemeister 2 are this, and type of crossing a little bit change. Please write down. And of course, but please let us try the relations for the third Reidemeister move. So you have this one and this one. Of course, actually, this may be too boring, but in reality, I should write down other possibilities with different orientations, and maybe this is going under and so on. So actually, schematically and ideologically it may be the same, but this may be more complicated. So here what we have, sorry, 1, 2, 3, 4, no, 1, 2, 3, 4, 5, 6. Here we have okay, other stuff anyway. So, but if you write down the relations and see that they are Titze equivalent to one to another, we'll complete the proof of the invariance of Vertinger presentation. Okay, that's all. Please, do you have any question?
No, it's okay.
Thank you.
Thank you.
Thank you.
Danke.